All right, this is lesson 2 on modeling covalent bonds. What we're going to do in this lesson is illustrate the sharing of electrons between atoms. Specifically, what we're talking about is non-metal atoms. We've learned so far that metal atoms form a sea of electrons when they bond, and metals and nonmetals transfer electrons, but nonmetals with nonmetals share. Now, the tool that we're going to use is an electron dot model. Electron dot models are also called Lewis dot models, or in other terms, Lewis structures. You need to be familiar with all 3 of these names because they're referring to the same tool which we're going to use. Now, that being said, what we want to be able to do successfully by the end of the lesson is explain how 2 nonmetals bond together, especially because it's the last scenario we see with bonds forming. Now, this illustration that I've got here is kind of a favorite of mine. I think it's so adorable, and it's actually going to show exactly what we're going to be talking about in this lesson today. So far, we've already talked about the first example here on the left and the middle example here. When we've got fluorine and fluorine bonding together, what you might notice about these 2 atoms is that they look exactly the same. Each fluorine atom has 1, 2, 3, 4, 5, 6 electrons to itself, while it shares 2 electrons with the other atom. In other words, what I'm seeing occur here is there's an equal sharing of electrons between both fluorine atoms. If I were to compare to the oxygen diagram, I'm seeing something very similar. It might not be the exact same amount of electrons being shared, but each oxygen has access to the same amount of electrons. In other words, the sharing is equal. But when I look over here at this last example, this is an example we haven't illustrated just yet. I've got a bond between sulfur and hydrogens. And what I'm clearly seeing is that there is sharing going on, but sulfur has access to more electrons than the hydrogens do. In other words, there's an unequal amount of sharing going on. Sulfur just simply has more electrons at its disposal than the hydrogens do. And that happens, but we need to know how to draw a dot model illustrating that. So that's really going to be our focus for this lesson. So let's get started. What we've talked about so far is that molecules follow the octet rule, which means that when nonmetals share electrons, they're doing so to get that full octet of electrons. We see this with carbon and hydrogen in the molecule CH4. We drew this in part 1 several times, actually. Now, we've got several options for illustrating electron dot models. Our favorite one, and maybe my favorite one, is option 1. Option 1, I feel, is a very clear depiction of exactly what's going on. What I can see is the overlap space between my carbon and hydrogen atoms, and I can clearly see the illustration of what electrons are coming from carbon and what electrons are coming from the hydrogens. Now, what we'll more often see is option 2. Option 2 is what we'll see in chemistry texts, on tests or exams, or maybe even in the textbook itself. Rather than showing overlap space and drawing the specific electrons, we represent those electrons as being shared with these bars. Now, those bars are great for doing this in a shorthand, quick fashion. What it's difficult to remember is that those bars represent 2 electrons. So sometimes it's kind of nice to just draw the 2 electrons on the bar, and that's something you might see me doing moving forward. Now, there's a third option that we haven't talked about just yet, but you will start to see it popping up every now and then. Option 3 is illustrated here on the right. Option 3 is simply a 3-dimensional or a 3D drawing of the molecule. What we see in option 3 is that there are some bonds, like the top one and the one to the right, that are flat on our page of paper. But there are other bonds that are 3-dimensional, like this bond down here on the bottom left. It's drawn with a really thick bar to illustrate that this bond is coming out of the paper towards you. And then the bond on the far left that's dotted is actually showing us that the bond is going into the paper away from us. You're not going to be required to draw bonds that are 3-dimensional, but you might be shown images of 3-dimensional bonds, and I don't want you to think that it means anything other than a single covalent bond. So if you see these bolded or dotted lines, just remember it's still a covalent bond. It still represents 2 electrons. All it's trying to show you is a three-dimensional picture. Now, what's nice about this model that we've used so far is that each atom is sharing electrons with the other. There's no extra leftover electrons. But what happens if electrons aren't shared equally? How would we illustrate that? Well, let's find out on some examples on the next page. When atoms don't share electrons equally, what we'll see is that one atom will hold onto lone pairs of electrons, whereas the other atoms don't. So if I'm looking at H2O, for example, H2O is water. Hopefully that's a formula you've heard before. What I can see in H2O is that hydrogen is sharing electrons with oxygen. However, oxygen has 2 extra pairs of electrons all to itself. This is an unequal sharing, and we illustrate that by just showing those lone pairs of electrons around oxygen. I also see this occur in other molecules like CO2. That might look familiar to you as well. CO2 stands for carbon dioxide. This is actually the gas that you breathe out every time you exhale. The oxygen atoms in carbon dioxide also keep pairs of electrons to themselves. These pairs of electrons that they keep, they don't share with carbon. It's an unequal amount of sharing because carbon shares all of its electrons and doesn't keep any lone pairs to itself. But we would show that unequal sharing by just drawing those extra pairs of electrons around the oxygen atoms. So essentially what we're going to be doing is illustrating extra pairs as lone pairs around specific atoms. So you'll hear me use the term lone pairs moving forward. All that I'm referring to is, again, these extra pairs of electrons that hang out around one specific atom. So let's try it with a couple of examples. The steps that we're going to be using are going to be the same steps as what we saw from part 1. So the first thing that I'm always going to do is add up the valence electrons from all the atoms in the molecule. So let's do that for this first example. Example 1. SH2 stands for sulfur and hydrogen, 2 hydrogens to be specific. Sulfur is in a specific group on the periodic table, group 16, which means it has 6 valence electrons. So I'm going to add sulfur's 6 valence electrons to the number of valence electrons each hydrogen has. Each hydrogen has 1 valence electron. Now, if I look in my molecule, that 2 there stands for 2 hydrogen atoms. So I'm going to add up 2 valence electrons for those 2 hydrogen atoms to get me a total of 8 valence electrons. Step 2 involves me actually drawing. All I'm going to do is form a bond between each pair of atoms in the molecule. So sulfur is going to be in the middle of the molecule, and I'm going to bond it to each hydrogen with a single bond. Step 3 involves me arranging the remaining electrons around the molecule. I'm going to arrange the remaining electrons in hopes of filling the octet rule for all of my atoms. So let's get started. I'm going to redraw my drawing from step 2, and I'm going to figure out how many electrons I've drawn so far. So far, each bond represents 2 electrons. So I've drawn 2, 4. I have to get to a total of 8, so I'm going to keep going. 2, 4, 6, 8 is my total. So I've drawn my total number of valence electrons. Now I just need to double check that I've satisfied the octet rule for all of my atoms. Let's start with hydrogen over here on the left. Hydrogen over here on the left requires only 2 electrons to get a full octet, and that's what it has access to, so that works out perfectly. Hydrogen over here on the right only requires 2 electrons as well, which is what it has access to. So that so far is satisfied, which leaves sulfur in the middle. My sulfur in the middle has access to 2, 4, 6, 8 total electrons, which is exactly what it requires. So my molecule is a completely drawn molecule now that all my atoms satisfy the octet rule. So I'll just redraw it a little bit more neatly here on the right. my molecule would look like this, and my sulfur would simply have 2 lone pairs all to itself. I'll box my answer, and then I'm ready to move on to the next. So let's try the next one together, and then you can try a couple on your own. I'm going to do the same 3 steps as I did for the last one. I'll start by adding up the number of valence electrons from silicon and oxygen. Silicon is in group 14, so it has 4 valence electrons, whereas oxygen is in group 16 and has 6 valence electrons. I'll add up 4 from silicon, 6 from oxygen, but I have to keep in mind that there are 2 oxygens in this molecule, so I need to add 6 twice to get me a total of 16 valence electrons. Step 2 is going to require me to connect everything with single bonds, and that's exactly what I've done. So now let's move on to step 3. In step 3, I'm going to start drawing my remaining pairs of electrons. Let's start by figuring out how many I've drawn so far. So far, I've drawn 2, 4, 6, 8. That's 8 more to go, so I'm going to draw the rest. I've got 2, 4, 6, 8, 10, 12, 14, 16. Great. There's my 16 electrons. Now let's see if my octet rule is satisfied. Oxygen on the right has access to 2, 4, 6, 8 electrons. That's perfect. Silicon in the middle has access to 2, 4, 6, 8 as well. That works out perfectly, leaving my oxygen on the left. However, oxygen on the left only has access to 2, 4. That's simply not enough. It needs to have an access to 8 total. So this is not the correct drawing for my molecule. I'm going to simply try again. This time, however, I'm going to use double bonds instead of single bonds. By using double bonds, I've definitely changed the number of electrons I've drawn to start with. So let's count. I've drawn 2, 4, 6, 8 total electrons. 8 means I've only got 8 more to get to 16. Now, since silicon has 8 around it, I'm going to draw my remaining electrons around the 2 oxygens. So I've got 8 so far. I'm going to keep going. 8, 10, 12, 14, 16. Okay, I've drawn my total 16. Now I just need to double check, does everything have access to 8 total? So my oxygen on the left has an access to 2, 4, 6, 8. That's perfect. Let's look at the oxygen on the right. Oxygen on the right has access to 2, 4, 6, 8. Perfect. Let's just double check silicon in the middle has access to 2, 4, 6, 8. Perfect. All my atoms satisfy the octet rule. So to draw my final picture in a neat manner, I'll just simply redraw it here on the right. Silicon double bonded to both oxygens, and both oxygens keeping 2 lone pairs to themselves. And that would be my final drawing. So go ahead and try practicing using these 3 rules on the next 2 tries. Pause the video and unpause when you're ready to check your answers. If you're watching this video, I'm assuming that you're ready to check your answer to the first try. Hopefully for step 1, when you added up your valence electrons, you got to a total number of 8. For step 2, when you connected everything with single bonds, you should have had phosphorus bonded 3 times to hydrogen. For step 3, we needed to redraw this and add any remaining electrons. So far, we've illustrated a total of 2, 4, 6, and that's it. We still need 2 more to get to 8. those remaining 2 electrons should go on the phosphorus. Why? So that phosphorus has a total access to 8 electrons. This would put everything in satisfaction of the octet rule. So my final diagram would look something like this. Phosphorus bonded 3 times to hydrogen with one lone pair of electrons kept to itself. That was a really bad box. There we go. Go ahead and attempt the next one and see if you get the correct answer. I'm going to assume if you're watching this, you're ready to check your answer to the next one. Step 1, you should have gotten 4 plus 6 plus 6 to get you a total of 16 valence electrons. For step 2, you should have started by single bonding carbon to both of the oxygens. For step 3, hopefully you noticed that you had some trial and error. When you started drawing your electrons, you should have noticed that you had already drawn 4 electrons, which leaves 12 more to get to 16. We could have drawn 4 more around oxygen, 6 around that oxygen, and then 2 around that oxygen. This would have gotten us to our total of 16. However, it would not have satisfied the octet rule. So we would have had to start all over again. And this time, we would have started by drawing double bonds. By doing so, this changes the number of oxygens or electrons that we've drawn to start with. I just realized that's not an O. Let's fix that. There we go. We would have drawn 2, 4, 6, 8, leaving us 8 more to draw. We can still fit 4 on the oxygen on the right and 4 on the oxygen on the left. This satisfies the octet rule, getting us to a total of 16 electrons, and this would have been our final drawing. So now that you've gotten some practice and confirmation that you are doing it right, we want to make sure that this skill becomes something that we can do comfortably and confidently. So practice moving forward is going to make this key. So go ahead and move on to the aligned practice that goes with this lesson.